Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Above our heads, beyond the familiar blue of Earth's atmosphere, lies the ultimate frontier that humanity has dreamed of exploring for generations. Space tourism, once confined to the realm of science fiction, has emerged as one of the most revolutionary industries of the 21st century. The concept transforms space from an exclusive domain of government astronauts and scientists into an accessible destination for civilian adventurers willing to invest in the experience of a lifetime. The journey toward commercial space travel began decades ago, but the industry's modern incarnation took shape in the early 2000s when visionary entrepreneurs recognized that space exploration didn't have to remain the sole province of national space agencies. Dennis Tito became the world's first space tourist in 2001, paying $20 million for an 8-day journey aboard a Russian Soyuz spacecraft to the International Space Station. This historic flight proved that civilians could safely travel to space, establishing the foundational precedent for today's burgeoning space tourism market. Currently, the space tourism market crossed $827.2 million in 2023 and is projected to observe around 36.5% compound annual growth rate from 2024 to 2032. This explosive growth reflects increasing technological sophistication and declining costs that make space travel more accessible to affluent individuals seeking unique experiences beyond Earth's boundaries. Leading companies in the space tourism industry include Virgin Galactic, Blue Origin, SpaceX, and Axiom Space, which offer suborbital, orbital, and private space travel experiences. Each company has developed distinct approaches to commercial spaceflight. SpaceX, founded by Elon Musk, has pioneered rocket reusability, significantly reducing the costs of space launches. This technological breakthrough represents a fundamental shift in how the industry approaches space transportation economics. Virgin Galactic focuses on suborbital flights using their unique Spaceship Two vehicle, which launches from a carrier aircraft at high altitude. Blue Origin employs their New Shepard rocket system for vertical takeoffs that carry passengers just beyond the Kármán line at 100 kilometers above Earth. These suborbital experiences provide approximately 3 to 4 minutes of weightlessness and spectacular views of Earth's curvature against the black of space. The current market dynamics reveal fascinating trends about consumer demand and technological capabilities. Suborbital stands as the largest component in 2024, holding around 52.5% of the market. This dominance reflects both the relative accessibility of suborbital flights compared to orbital missions and the compelling experience they provide for passengers seeking their first taste of space travel. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The technological foundations supporting space tourism rely on decades of aerospace engineering advances, sophisticated safety systems, and rigorous testing protocols. Companies must navigate complex regulatory frameworks while developing vehicles capable of safely transporting civilians who lack the extensive training traditional astronauts receive. This challenge has driven innovation in automated flight systems, simplified passenger interfaces, and comprehensive safety redundancies that protect travelers throughout their space journey. Looking at the broader implications, space tourism represents more than recreational adventure. It signals humanity's transition toward becoming a spacefaring civilization. Each successful commercial flight demonstrates that space travel can become routine, safe, and economically viable for growing numbers of people. This democratization of space access could fundamentally reshape how humanity views its relationship with the cosmos and our planet's place within it. Understanding space tourism requires grasping the fundamental physics that govern how humans escape Earth's gravitational embrace and experience the unique environment of space. The journey from Earth's surface to the edge of space involves overcoming immense physical forces and navigating through distinct atmospheric layers, each presenting unique challenges for spacecraft and their passengers. Earth's gravitational field exerts a constant downward acceleration of 9.8 meters per second squared on all objects near its surface. To reach space, vehicles must achieve sufficient velocity to counteract this gravitational pull. For suborbital flights, spacecraft need to reach approximately 3.7 kilometers per second, while orbital missions require velocities exceeding 7.8 kilometers per second, the minimum speed necessary to maintain a stable orbit around Earth. Rocket propulsion systems achieve these incredible velocities through Newton's third law of motion. For every action, there is an equal and opposite reaction. Rockets expel high-velocity exhaust gases downward, generating thrust that propels the vehicle upward. The relationship between thrust, mass, and acceleration determines how quickly spacecraft can gain altitude and velocity. Modern space tourism. Vehicles employ various propulsion technologies, from traditional chemical rockets burning liquid or solid fuels to hybrid systems that combine different propellant types for optimal performance and safety. The atmosphere through which space tourists travel consists of distinct layers, each characterized by specific temperature, pressure, and density profiles. The troposphere extends from sea level to approximately 12 kilometers altitude, containing roughly 80% of atmospheric mass and virtually all weather phenomena. Above this lies the stratosphere, reaching 50 kilometers altitude, where the protective ozone layer absorbs harmful ultraviolet radiation from the sun. As spacecraft ascend through the mesosphere, from 50 to 80 kilometers altitude, atmospheric density decreases dramatically. The thermosphere extends from 80 kilometers to approximately 600 kilometers, where temperatures can reach 1,500 degrees Celsius due to solar radiation absorption, though the extremely thin air cannot effectively transfer this heat to solid objects. The Kármán line at 100 kilometers altitude represents the internationally recognized boundary between Earth's atmosphere and outer space. Achieving weightlessness represents one of space tourism's most profound experiences. Contrary to popular belief, weightlessness doesn't result from escaping Earth's gravity. Gravitational force remains strong even at the International Space Station's altitude of 400 kilometers. Instead, weightlessness occurs when spacecraft and passengers fall freely around Earth in a continuous state of free fall. During suborbital flights, passengers experience true weightlessness for several minutes as their vehicle follows a parabolic trajectory, reaching maximum altitude before beginning its descent back to Earth. The physics of weightlessness creates fascinating phenomena that tourists find both exhilarating and disorienting. Without gravitational reference, human bodies lose their sense of up and down. Fluids behave differently, water forms perfect spheres, flames burn in spherical shapes, and even tears don't fall from eyes. These effects result from the absence of buoyancy forces that normally separate materials of different densities on Earth's surface. Spacecraft design must account for the extreme environmental conditions encountered during spaceflight. Vehicles experience rapid temperature variations from -270 degrees Celsius in Earth's shadow to +120 degrees Celsius in direct sunlight. The vacuum of space eliminates air resistance, but also prevents conventional cooling through convection, requiring sophisticated thermal management systems to maintain comfortable cabin temperatures. Atmospheric re-entry presents additional technical challenges as spacecraft returning from space must dissipate enormous kinetic energy while protecting passengers from extreme heating. Vehicles typically enter Earth's atmosphere at speeds exceeding 25,000 kilometers per hour, creating plasma sheaths around their surfaces with temperatures reaching several thousand degrees Celsius. Heat shields and controlled descent profiles ensure passenger safety during this critical phase of flight. The G-forces experienced during launch and re-entry significantly exceed those encountered in normal terrestrial activities. Space tourists typically experience 3 to 6 times their normal body weight during powered ascent, followed by the sudden transition to weightlessness. These acceleration forces require careful management through spacecraft design, passenger positioning, and flight profiles that minimize physiological stress while maintaining safety margins. Understanding these scientific principles helps appreciate the remarkable engineering achievements that make space tourism possible and safe for civilian passengers. The contemporary space tourism landscape features several pioneering companies, each employing distinct technologies and flight philosophies to deliver unique experiences for their passengers. These organizations have invested billions of dollars developing specialized vehicles, safety systems, and operational procedures that transform the theoretical possibility of civilian space travel into tangible reality. Virgin Galactic operates the world's first commercial space line, utilizing their innovative Spaceship Two vehicle system for suborbital flights. Their approach employs a unique air launch methodology, where the Spaceship Two passenger vehicle, carried by the White Knight 2 mothership, releases at approximately 15 kilometers altitude. The passenger craft then ignites its hybrid rocket motor, burning a combination of solid fuel and liquid oxidizer to accelerate vertically towards space. This design provides several advantages: reduced fuel requirements compared to ground-launched rockets, smoother initial ascent through lower atmospheric layers, and enhanced safety through the ability to abort missions before rocket ignition. Spaceship Two accommodates 6 passengers plus 2 pilots in a spacious cabin featuring large windows designed to maximize viewing opportunities. The vehicle's feathering system, inspired by badminton shuttlecocks, rotates the tail section upward during re-entry, creating natural stability and reducing heating through atmospheric friction. Passengers experience approximately 4 minutes of weightlessness while reaching altitudes exceeding 100 kilometers, providing spectacular views of Earth's curvature and the blackness of space. Blue Origin's New Shepard system represents a different technological approach, employing a traditional vertical launch rocket configuration. Their vehicle consists of a reusable booster rocket and a crew capsule designed specifically for passenger comfort and safety. The booster burns liquid hydrogen and liquid oxygen propellants, achieving high efficiency and minimal environmental impact compared to other rocket fuels. After separation at approximately 75 kilometers altitude, the crew capsule continues ascending on a ballistic trajectory while the booster returns to Earth for propulsive landing and reuse. The New Shepard crew capsule features the largest windows ever flown in space, each measuring over 1.1 meters tall and nearly 70 centimeters wide. These panoramic viewing ports provide unobstructed views in all directions, allowing passengers to observe Earth, space, and their fellow travelers during the weightless portion of flight. The capsule's automated flight systems require no pilot intervention, allowing all 6 seats to accommodate paying passengers rather than professional crew members. SpaceX approaches space tourism through their Dragon spacecraft, originally developed for NASA cargo and crew missions to the International Space Station. Their Inspiration 4 mission, in 2021, demonstrated the feasibility of all civilian orbital flights, with 4 private passengers spending 3 days orbiting Earth at altitudes exceeding 500 kilometers. This orbital approach provides dramatically longer space exposure, 72 hours versus 4 minutes for suborbital flights, and allows passengers to experience extended weightlessness, Earth observation opportunities, and the psychological impact of truly leaving Earth behind. The Dragon spacecraft launches atop SpaceX's Falcon 9 rocket, which employs advanced propulsive landing technology to return both first-stage boosters and crew capsules for reuse. This reusability significantly reduces per-flight costs while demonstrating the reliability necessary for safe passenger operations. Dragon's life support systems can sustain crew members for up to 7 days, providing substantial operational flexibility for various mission profiles. Axiom Space focuses on orbital tourism through partnerships with SpaceX and plans for their own commercial space station. Their approach targets longer duration experiences, with missions lasting 8 to 10 days aboard the International Space Station. Passengers undergo several months of training, including spacecraft systems familiarization, emergency procedures, and scientific experiment protocols that allow them to contribute meaningfully to orbital research activities. Emerging competitors continue entering the space tourism market with innovative approaches. Space Perspective develops stratospheric balloon flights that carry passengers to 30 kilometers altitude in pressurized capsules, providing space-like views without the physical stresses of rocket propulsion. Worldview Enterprises pursues similar balloon-based tourism, while companies like Orbital Assembly Corporation design rotating space stations that could provide artificial gravity for extended orbital stays. The technological diversity among these companies reflects different philosophies about optimal passenger experiences, safety approaches, and market positioning. Suborbital flights prioritize accessibility and dramatic but brief experiences, while orbital missions offer extended space exposure at significantly higher costs and training requirements. This variety ensures that space tourism can accommodate diverse passenger preferences, physical capabilities, and financial resources as the industry continues maturing and expanding its customer base. Space tourism, despite its remarkable technological achievements, presents numerous challenges and risks that companies must carefully address to ensure passenger safety and mission success. The extreme environment of space imposes unique physiological and psychological stresses on human beings, while the complex engineering systems required for spaceflight introduce potential failure modes that could prove catastrophic without proper preparation and redundancy. Microgravity effects, experienced during the transition to and from microgravity environments, can cause motion sickness, disorientation, and physiological changes in the human body, requiring proper preparation and support. Space adaptation syndrome affects approximately 50% of space travelers, causing symptoms ranging from mild nausea to severe vomiting that can persist for several days. While suborbital tourists experience weightlessness for only minutes, the sudden transition from normal gravity to free fall and back again can trigger vestibular system confusion as the inner ear struggles to maintain spatial orientation. Microgravity can cause various physiological changes, such as bone loss, muscle atrophy, fluid shifts, and vision problems. During weightlessness, bodily fluids redistribute toward the head and torso, creating facial puffiness and sinus congestion that many space travelers find uncomfortable. This fluid shift also affects cardiovascular function, as the heart must adapt to pumping blood without gravitational assistance. While short-duration suborbital flights minimize these effects, orbital missions lasting days or weeks can produce more pronounced physiological changes. Radiation exposure can increase the risk of cancer and damaged DNA, representing a particular concern for extended orbital flights. Earth's magnetic field and atmosphere provide natural protection against cosmic radiation and solar particle events. However, spacecraft operating above the atmosphere encounter significantly higher radiation levels, especially during solar storms, when charged particle flux can increase dramatically. The effects of space exposure can result in embolism, hypoxia, hypocapnia, and decompression sickness if cabin pressurization fails or passengers are exposed to the vacuum of space. Spacecraft malfunctions, including failures in life support, navigation systems, present serious risks requiring comprehensive emergency procedures and backup systems. Life support failures could rapidly become life-threatening as oxygen supplies dwindle or carbon dioxide levels rise to dangerous concentrations. Navigation system failures might prevent spacecraft from achieving proper trajectories for safe Earth return, potentially stranding passengers in space or causing them to re-enter Earth's atmosphere at incorrect angles that could prove fatal. Psychological challenges affect some space tourists despite thorough pre-flight preparation. The overview effect, a cognitive shift that occurs when viewing Earth from space, can produce profound emotional responses ranging from euphoria to existential anxiety. Some passengers experience claustrophobia in spacecraft's confined spaces, while others develop acute awareness of their separation from Earth's protective environment. The isolation and unusual sensory environment of space can trigger panic responses in susceptible individuals. Safety protocols employed by space tourism companies include extensive medical screening to identify passengers with conditions that might be exacerbated by spaceflight stresses. Cardiovascular disease, respiratory problems, and certain medications can disqualify potential space tourists. Pre-flight training programs familiarize passengers with spacecraft systems, emergency procedures, and the physical sensations they'll experience during launch, weightlessness, and re-entry phases. Maintaining a safe ecosystem inside a spacecraft presents unique challenges, from ensuring optimal temperatures, pressures, and lighting, to reducing noise, monitoring microbial communities, and tracking immune responses. Spacecraft environmental control systems must maintain precise atmospheric conditions while managing waste products, humidity levels, and air quality in closed-loop systems with no possibility for outside air exchange. Regulatory frameworks governing space tourism continue evolving as government agencies balance public safety concerns with industry growth objectives. The Federal Aviation Administration oversees commercial space launches in the United States, requiring companies to demonstrate their vehicles meet specific safety standards and obtain licenses for each mission. However, current regulations place primary responsibility for passenger safety on the companies themselves, rather than imposing detailed safety requirements similar to those governing commercial aviation. Emergency abort systems represent critical safety features that allow spacecraft to separate passengers from malfunctioning rockets during launch phases. These systems must function reliably under extreme conditions, including high acceleration forces, vibration, and potential explosive environments. Crew capsules require independent life support, navigation, and landing systems to ensure passenger survival even if primary spacecraft systems fail completely. Training requirements vary significantly among space tourism companies, from brief orientation sessions for suborbital flights to months-long preparation programs for orbital missions. More extensive training generally correlates with longer space exposure and more complex spacecraft systems that passengers might need to operate during emergencies. The inherent risks of space tourism require continued technological development, rigorous safety protocols, and transparent communication with potential passengers about the challenges they may encounter beyond Earth's protective atmosphere. The future of space tourism extends far beyond today's brief suborbital flights and short orbital excursions, encompassing revolutionary developments that could transform space travel from an exclusive luxury into an accessible experience for millions of people. Technological advances, economic trends, and ambitious infrastructure projects are converging to create possibilities that seemed purely fictional just decades ago. Increasing investments by billionaires and private companies spur market expansion, reaching revenues of $6.7 billion by 2030, indicating the industry's trajectory toward mainstream acceptance and economic viability. This growth reflects not only increasing consumer demand, but also fundamental improvements in spacecraft technology, manufacturing processes, and operational efficiency that drive down per-flight costs while improving safety margins. Reusable. Rocket technology represents the cornerstone of future cost reductions in space tourism. Companies are developing increasingly sophisticated systems that can perform dozens or hundreds of flights with minimal refurbishment between missions. SpaceX's Falcon 9 first stages have already demonstrated this concept, with some boosters completing over 15 successful flights. Future vehicles will push reusability even further, potentially reducing launch costs by factors of 10 or more compared to expendable rockets. Advanced propulsion systems under development could revolutionize space tourism by dramatically reducing flight times and expanding accessible destinations. Hair-breathing engines that operate efficiently both within Earth's atmosphere and in space could enable single-stage-to-orbit vehicles that eliminate the complexity and expense of multi-stage rockets. Nuclear thermal propulsion systems could power rapid transit to the Moon, reducing journey times from days to hours while carrying larger passenger loads. Space hotels and orbital facilities represent the next major milestone in space tourism infrastructure. Several companies are developing commercial space stations designed specifically for tourist accommodation. These facilities will feature artificial gravity through rotation, luxury amenities, and panoramic viewing areas that provide continuous Earth observation opportunities, Gateway Foundation's planned rotating space station could accommodate hundreds of guests in hotel-like accommodations, with restaurants, recreational facilities, and even sports venues adapted for low-gravity environments. Lunar tourism emerges as space technology matures and costs decrease. SpaceX's Starship vehicle, designed for eventual Mars missions, possesses sufficient capability to transport passengers around the Moon or even land on the lunar surface. Such missions would provide experiences impossible to replicate near Earth, viewing Earth as a small blue marble against the cosmic backdrop, exploring alien landscapes under 1/6 gravity, and experiencing the profound isolation of humanity's first steps beyond our home planet's immediate vicinity. Manufacturing in space could create entirely new categories of space tourism experiences. Orbital factories producing unique materials, impossible to create under Earth's gravity, could attract industrial tourists interested in witnessing zero-gravity manufacturing processes. Space-based research facilities might offer scientist tourists opportunities to conduct experiments in microgravity environments, combining recreation with meaningful scientific contribution. Transportation infrastructure connecting Earth and space will expand beyond simple point-to-point rocket flights. Space elevators, while still technologically challenging, could eventually provide low-cost, high-frequency access to orbit through mechanical systems rather than chemical propulsion. Orbital rings or other megascale engineering projects might create permanent transportation networks that make space travel as routine as international air travel today. The democratization of space access carries profound societal implications. As costs decrease and safety improves, space tourism could become accessible to middle-class families rather than only billionaires and millionaires. This accessibility would expose millions of people to the overview effect and the profound perspective shift that comes from seeing Earth as a single fragile oasis in the cosmic void. Such widespread space experience could fundamentally alter humanity's relationship with our planet and our understanding of our place in the universe. Educational space tourism could transform how humans learn about science, technology, and our cosmic environment. Students might take field trips to orbital laboratories, while researchers could conduct experiments impossible on Earth's surface. These experiences would inspire new generations of scientists, engineers, and explorers, while advancing human knowledge through unique research opportunities. Long-term prospects for space tourism include permanent space settlements where people live and work rather than simply visiting. These communities would develop their own cultures, economies, and social structures adapted to space environments. Multi-generational space habitation would create truly spacefaring human populations with perspectives and capabilities shaped by life beyond Earth. The convergence of artificial intelligence, robotics, and space technology will create increasingly autonomous systems that reduce the skill requirements for space travel while improving safety and reliability. Future space tourists might travel in spacecraft that require minimal human intervention, with AI systems managing complex flight operations and emergency responses more effectively than human pilots. Space tourism's evolution from experimental adventure to routine transportation represents humanity's first steps toward becoming a multi-planetary species, forever changing our relationship with the cosmos and our understanding of human potential.